Well, probably we ought to start since it's 9:40. So, announcements. Rashad is doing office hours again today after class, and I think he may have another problem set graded for you guys. And so he posted that on Blackboard. And I also updated Professor Watson's office hours, and he's doing Thursday 1 to 3 henceforth, I think. And so you guys are welcome to stop by his office today, which is really nice. So, and maybe by next week I'll be able to do office hours, or at least by Zoom. Okay, so I think that's mostly announcements. Oh yeah, so for those of you who didn't find the recordings of these lectures, not that they're all that great, but they are posted on the class website, and the link is available through Blackboard, but you can also just go to the class website, and at the top, one of the, there is a link saying recordings. So if you want to find the recordings, they exist. Okay, I have been posting them, and some students have found them, so other students did not find them. Okay, so let's move on to what we were talking about last time. So last time we were talking about the system where we had two masses and they're the same. And they're on this horizontal, like frictionless surface, and there's a spring between them, which has a spring constant K. And we defined this distance between them, D. And then XA and XB are the positions of the two masses. And so we had found the equations of motion for the system. The only force here, since we're ignoring gravity, is the spring, but we gave the spring a rest length. And so the equations of motion were this. Minus K times XA minus XB plus L. And then there was an equal and opposite force on the other mass. And L is the rest length of the spring. Okay. So, yeah, so one way to make this, let's make this darker color so it's easier to see. One way to make this problem easier is to look at what happens to the center of mass and what happens to the distance in between the two masses. And so we had a center of mass position. So since the masses are equal, it's just, wait, what's this? Let's erase that. It's the position of the first one plus the position of the second one divided by 2, because they're equal masses. And then the distance in between them, we just did this way. That's pretty straightforward. And the inverse transform, so if we have the center of mass position and the distance in between them, it's pretty straightforward. Whoa, why did it do that? The problem I'm having is that I can't hunch over, otherwise my shoulder hurts. And so when I rest my hand, it does bizarre stuff. Okay, so let's get the inverse transform. It's the center of mass position minus D over 2. And the other one is the center of mass position plus D over 2. And if you add these together, you can see that the transformation and the inverse transformation are consistent. So taking the equations of motion last time at the end of lecture, we added them together. And because the spring force were equal and opposite, when you add the two equations of motion together, you get this equals 0. And this we can write as d squared x center of mass dt squared equals 0. So there's no acceleration on the center of mass. It drifts forever. So this is not really surprising, because this is a situation where we have equal and opposite for internal forces. And in that setting, the center of mass is not affected. But this means that we know the center of mass at all future times because we can solve this. So we can write the center of mass, the solution to this equation is that it's some constant at 0 plus the center of mass velocity times time. And that's the solution for the center of mass at all future times. So instead of adding the two equations of motion, we can subtract them. And if you do that, you get this. You get an equation for the distance between the two masses that looks like this. So I'm kind of skipping a few steps. So let me write out what you actually get, and then it will turn into this. What you actually get is this when you subtract the two equations of motion. 2k over m. Because now instead of the forces canceling each other, they add. So you get this factor 2 here. And then we have xb minus xa minus l. And so this is d, and this is d, and this is that. So it's 2k over m. So, so for a harmonic oscillator, normally you have omega is square root of k over m. So let's write this more like, I can get rid of that and put this like that. So normally it's square root of k over m. But if we wrote this frequency in terms of the reduced mass, so let's just go to a new view graph. So supposing I write the reduced mass, so since I have two equal masses, it's m over m plus m. And this is equal to m over 2. So omega, which looked like this, k over m, I can also write like this. So not surprising. So yeah, so that's the equivalent. So this is more general. I mean, we could actually, instead of starting with two equal masses, we could say, what if we had two unequal masses? We could also solve the problem, but we'd have to do a little bit more in order to get to add and subtract the equations of motion. We would have to be doing a little bit of weighting with the masses, and then we would pick up the reduced mass. So this would be a more general. If we solve the more general problem, the frequency would be this. Okay, so let's go back to the equation of motion for the distance in between the two masses. And we get, so I'm just going to write it down again. So this thing, the solution to this is d, no, not d. Solution to this is L plus something that it's a harmonic oscillator. So if I subtracted, if I got rid of L, this would be the equation of motion for a harmonic oscillator. So if you guys remember, a harmonic oscillator looked like this. Squared there. So the distance between the two masses obeys the same equation of motion as a harmonic oscillator. And so that means we know the general solution at all later times. We can write it in terms of a cosine omega t plus a sine omega t. So that's a general solution. And we just have to find A and B. And so let's summarize what we have now. We have general solution for the center of mass, and we have a general solution for the distance in between them. Both of them involve two constants. So for the center of mass, so I guess I can go back. Where did I write the center of mass? Here, yeah. So here's the equation of motion for the center of mass. There's a constant, which is the initial center of mass position, plus the center of mass velocity, which is constant. And then for the distance in between them, we have this constant and that constant. So there are four constants that will determine the equations of motion forever. or the solution forever. So let's now actually do an initial conditions problem. So if we start off with initial conditions, we can find those constants, and then we can write down the solution forever. So, suppose the position of the first mass is initially at 0, and the position of the, so what I want actually, let's write what I meant here is this, t equals 0 equals 0. And the position of the second mass, I'm just going to give it L. And this is not information, it's only two things, so we need to specify initial velocities too. And so I'm just going to give this a negative v0, and the initial velocity of the second mass, I'll get that, set that one to be 0. So, so let's figure out what's the center of mass is doing. So the initial center of mass position, I just have to add these two guys and divide by 2. So it's L over 2 because they're equal mass. So, to be more specific, it's m times this one, which is 0, plus m times this guy, which is L, divided by the 2 masses, right? So that's equivalent. So what about the velocity of the center of mass? So this is going to be a constant, and it's going to stay fixed forever, but, just write it as an initial condition. So again, we just have to weight the 2 velocities, so it's minus v0 over 2. Okay, so now we know the center of mass position at all later times. So it's the initial one, which is L over 2, minus the velocity of the center of mass times time. Oh, yeah. So this is center of mass at later times. Okay, so we solved that part of it. Now we need to find the solution for the distance between them at all later times. So the distance between them at t equals 0 is just this xb minus xa, which is L. And but I also need the velocity, so d, big D dt at t equals 0 is vb minus VA, which is equal to V0 because VA is minus V0. So, so I have the initial distance between them and the initial time derivative of the distance between them. So, so now let's recall our solution for the distance between them is L plus A cosine omega t plus B sine omega t. So D at t equals 0 is L plus A, and d dt. So let's take the time derivative of this. L goes away. A omega sine omega t, cosine goes to minus sine, plus B omega cosine omega t. So d dt at t equals 0 is equal, so the sine of 0 is 0 is equal to B omega. So this has to be, so looking back at what we had on our previous thing, we had d of t equals 0 is L, and d dt equals is, so this thing and this thing, B0. So let's go back here. So this is going to equal L, and that implies that A equals 0. And this is going to equal to V0, and that implies that B is equal to V0 over omega. And so now we can go back and plug in the for the distance between the two masses at all later times. So this thing is 0, we just found that, and B is V0 over omega, and we have sine omega t. And so that's the solution. So this is distance between masses at all later times. So supposing we now want to actually figure out the position of each mass at all later times. All we need to do now is use the transform. So we had, remember I wrote down the transform. So let's show that here. So this at the top was a center of mass position in terms of the two particle positions and the distance between them. This is the inverse transform. So if I have the center of mass and I have the distance between them, I can get position XA and XB. So let's go in here. So this is exactly what we've got. Here's the distance between them. And then on the previous thing, we had the center of mass position at all later times. So we can use the inverse transform to write down the position of both masses at all later times. So here's the inverse transform. Now I'm just going to plug in what we got for both of those. Minus V0 over omega sine omega t minus L over 2. Of course, these L's over 2 cancel, but if you want to simplify it, you can. And here's the position for the other mass. It's plus d t over 2, which is equal to L over 2 minus V0 t over 2. Yeah, there's probably a 2 here. Plus V0 over 2 omega sine omega 2 plus L over 2. So I think there's a mistake in my solution on my notes. Okay, so that's the solution for both masses positions at all later time. So why do this long problem? So this long problem is kind of meant to illustrate that there's advantages to going in and out of this center mass description. And so this particular problem is just a molecule moving by itself, but it illustrates this idea that, if you want to, you can get the positions of the individual particles at all later times, but it's easier to solve the problem in the center mass frame because the center of mass drifts. So it's often easier to work in the center of mass frame. So that's kind of the point of this example. It's also practice at, using initial conditions and reminding yourself what harmonic oscillator solutions look like, stuff like that. Okay, so that concludes this example. And so I'm going to skip the next example, which is a more complicated jumper system, and talk about systems where you have kind of mass flow, actually. So some examples of mass flow. So the next example I want to talk about is a conveyor belt. So let's draw a conveyor belt. We have 2 wheels, and then there's a belt on it. And then I have like a hopper up here. And the hopper's full of some sand or something like that, or some kind of granular material. And that is going to dump onto the conveyor belt. And the conveyor belt is going to move this granular material, and then it's going to fall off into some pile at the end. So the velocity of the conveyor belt, we'll say, is v, and it's moving this way. And because, so the sand coming down off the conveyor belt is initially still, but the conveyor belt has to push the sand. And so there's some force here, F, which lets the sand move at velocity v. And so our goal is to figure out what force you need to move the sand, to move the conveyor belt at velocity v. And this is going to depend on how fast the sand is falling onto the conveyor belt. So, so we have a conveyor belt. The mass flow rate is dm dt. That's how fast the sand is falling onto the conveyor belt. And it's also how fast the sand is moving off to the other side into this pile. So our question is, what force do you need? So yeah, so the way to think about this is just think about over a small period of time, when the sand, how much over a small period of time. So if we have a dt, then a dm hits the conveyor belt. And once it's on the conveyor belt, it just stays at velocity v. So this dm has to be accelerated so it becomes gets a velocity v. So the change in momentum dp exerted by the conveyor belt to speed up this little dm to velocity v is dmv. And so so this, now we can both divide both sides by t, and you get dp dt is equal to v dm dt. So this is the force exerted by the conveyor belt in order to accelerate the these little parcels of mass falling onto it to velocity v. And so this has to equal the force. So that actually is the answer. So one way to think about this is if you draw like an arrow here like this is all in steady state. So so really it just comes down to accelerating the parcel that is falling onto the belt, because everything in here is fixed, meaning nothing's moving after you've accelerated the little parcel of mass. So this is actually the answer. Of course, is equal to v times dm. Okay, so that's the example of the conveyor belt. So now let's talk about thrust. So what do we mean by thrust? So thrust, you've got this rocket. Let's draw some cute little rocket, the little flames down here. And so the rocket has a mass m and a velocity v. And there's some mass outflow rate coming out here, and it's moving at a velocity v rel. So v rel is velocity of the propellant with respect to the rocket. And so because the rocket is expelling material, that's going to push it forward. And so there's a thrust force that's making the rocket go up, which is related to the outflow rate for the propellant times the relative velocity. And so if I've drawn the relative velocity in this direction, then the thrust is an opposite direction. So you get a minus sign here, and these can be vectors like that. So I actually have to correct my notes because there's some sign errors in there. But yeah, this is what there should be this sign where the thrust is in the opposite direction as the relative velocity of the propellant. Okay, so why does this make sense? Let's go back here and we'll talk about that. So again, you have to think about a small length of time t dt, and so because this is relative to the rocket, the propellant has to be accelerated so it reaches a different velocity than the rocket. And so the change in momentum for a little parcel of mass, dm, is equal to dm times the relative velocity. And that means the change in momentum is dm dt v rel. So, so I wrote it as big M here. Probably I should be consistent and write with dm with this little m instead of big M. So this is the, the propellant outflow rate. Right. So since this is the force you need to accelerate the propellant so that it's at this relative velocity with respect to the rocket, that means, I mean, there has to be an equal and opposite force. And so that means the thrust is actually the same thing. Why is the mass changing at all? So, yeah, so the idea is the rocket is expelling something, like it's burning something and gas is coming out. And so if you burn something, gas can come out at a high velocity and you don't use too much mass. But you could just have a puff of gas. So if you look at, so sometimes people with satellites, they can call them burns if they're heating up what's being expelled. But also rockets can adjust their altitudes and stuff with little puffs of gas too. And then you don't necessarily need a high velocity, but the fact that you're actually ejecting something is important. So yeah, so that means the mass of the rocket, yeah, okay, good. The mass of the rocket could be changing in time, actually. And so that doesn't mean this thrust is wrong. It's actually correct. It just means that if you wanted now to predict where the rocket's going, like how fast it's going as a function of time, you need to take into account that you're losing mass. Like, so the thrust is always equal to this. But that is equal to m dv dt, where m is the mass of the rocket, which could be changing in time because you've lost propellant. And so so this is actually something to optimize when you think about how do I most efficiently get a rocket in space? Do I want to burn a whole lot at the beginning, or do I want to burn a little bit and then increase it? So generally, to get out of the gravity well, yeah, wasn't the original m. So so m is the mass of rocket, but m could be a function of time because you're expelling some mass in the propellant. So so you could take that into account if you want to actually predict what about little m? So little m is the mass outflow rate. So that's how much mass is being expelled by the rocket. It's actually the same thing as dm dt. Little dm dt is equal to dm dt. Maybe I should have kept them the same symbol here. Maybe with a minus sign. Okay, good. So that's the idea. So let's think about this again. Does this really make sense, right? So I remember when I was an undergrad, I was always confused. So I can tell you what's thoroughly wrong. So what's thoroughly wrong is to think about dp dt. So let me write down what's really wrong. dp, so p is equal to mv, and dp dt, so is not this. If you use this, to try and figure out what's going on, you're going to get the wrong answer. So I remember doing this by mistake. So this is not right. So let me show you why it makes sense with what we did before. So it comes down to keeping track of the total momentum. So suppose we take, so we have a mass m for the rocket. Yeah, why is it wrong? So it's because it's not consistent with conservation momentum. So so if we have the mass of the rocket, and then we're going to expel a little mass dm, the initial total momentum, taking into account both rocket and this little bit of mass that we're going to expel, is this. So this is before expelling dm. Then later we've got m plus or mv plus dv, because the rocket is going to change velocity a little bit, plus dm, and the dm, it has a relative velocity of v rel after we've expelled it. So now we just set these two things to be equal. So m plus dm times v is equal to mv plus mdv plus dmv plus dm v rel. And so we can cancel this with this, and we can cancel this with this, and we get that mdv is equal to minus dm v rel. And that means that m dv dt is equal to minus dm dt times v rel. And that's equal to the thrust. So this is the same as we got before, where thrust is equal to the relative velocity times the outflow rate. And this is just the force on the rocket. So conservation of momentum gives you this. So you just have to be careful about this, right? So that's why that equation arises. Okay, so yeah, don't just blindly differentiate momentum, because you have to be careful when you do that if you're going to let the mass change. Okay, what is the letters between V? Letters between V. Before what? I don't know what you're talking about. After? Oh, okay. So this here, this was the before expelling, and this is after expelling. So after expelling, the mass of the rocket is changed by dV, this big V, and the little bit of propellant changes so that it has a relative velocity v plus v rel. So this is the relative velocity. So it's this, v rel, remember, is the velocity with respect to the rocket. And so this is the momentum after expelling the little bit of propellant. And because momentum, so the forces in between the propellant and the rocket are internal. So there's no external forces on this. So these two have to be the same. So P0 has to be equal to P1. And that's where I put this equation in, calculated some terms, and then you can find the force on the rocket, which is mdv dt, has to equal the thrust coming from the propellant. Okay. Okay, good. It's actually good to get interrupted, I appreciate it. Okay, so now we're going to go back to energy. Energy. So let's talk about energy. And we did it again. Energy of multi-particle systems. So, so what I want to talk about is gravitational potential energy. Now let's do an extended body. So if we have an extended body, the total mass is just the integral of density over the volume of the object. So we can write it like that. So remember dv. So now dv is not a change in velocity. It's a volume elements here, even though it looks the same. So it's dx dy dz volume element. So so with gravitational potential energy only depends on height. Remember, it's rho g, it's g times z, mgz for a point mass. We did that last week, or actually did that last week with Dan 2 weeks ago. So yeah, so what we're going to find out is that it doesn't really matter. The mass distribution doesn't matter. All it matters is center of mass. So let's the only component of the center of mass that we're going to care about is the z component, because potential energy depends on z. So let's recall what the z component of the center of mass looks like this: rho z dv. So you integrate up the mass distribution multiplied by z, and then you divide by m so that it's in units of distance. So the potential energy is of this, we can integrate it up, rho g z. So this is dv. So this is like rho dv is like a little mass element times z, and then this g, that's the gravitational acceleration. And so this is a so this would give you the total potential energy. But looking at this, so I can write z, let's take this equation and rewrite it a little bit. Just move the m to the other side. And so if I take this g out, you can see it's the integral of rho z dv. So that's this. What's rho? Rho is mass density. So once I move this g out, you can recognize this. It's the same thing. So the potential energy of an extended mass only depends on its total mass times the center of mass position. The center of mass z component of the center of mass position. Okay, so so that means if we wanted to think about the total gravitational force, it's really annoying that it does this. It keeps changing into highlighter mode. So I can integrate up rho dv times the force on as a function of position. Force for gravity is it's constant, doesn't really depend on anything. But this I could write as minus du d center of mass position. So this is equivalent because u is equal to gmg as not x, z center of mass. Yeah. So the force from gravity on an extended mass is equivalent. This whole, you can think of the potential energy, since it only depends on the center of mass position. There's nothing inconsistent with this. Thinking about it this way. Okay, so now I need to let's see, how do I? Is there some way to erase? So it won't let me make new ones, but I kind of remember I can. There's some way to, there's some way to vaguely thought there was some way to delete things. No, I can't figure out how to do that. Okay, we'll just get out of this then and get back in. It's kind of annoying that I have to keep doing this when you get to 12. Okay. I did figure out a way to delete them, but I've forgotten how it works. Okay, so moving on. So let's talk about, so gravity, you can think of as an external force. So in this, when we talked about potential energy of gravity only depends on Z center mass, you can think about that as an external force on an extended mass distribution. So we're going to talk about this a little bit in more generally. So supposing we have an external force on a multiple particle system. And so we can think about, we can calculate the work on the center of mass. So the momentum, so I'm going to do a non-relativistic setting. We can, so this is the total momentum. So you added up the momentum of every particle. I can write this, it's equivalent to mv v center mass, where m is the total mass. So the change in momentum, the total momentum, is equivalent to the change in the sum of the changes of the individual momentums, which is also equivalent to the sum of the forces on each particle. So let's consider a total force where we just sum these like this. And now let's look at this work that comes from integrating up the total force times the change in the center of mass position. So this is a vector, but now this is work. So I'm going to rewrite this and put it on another view graph because I need a little bit of room. So the force, total force, I can write as the time derivative of the total momentum. And I can multiply and divide by time. And dp dt, I can write out as m dv center mass dt, and dx center mass dt is equal to the center mass velocity. And if you look at this, I can write this like this. So m, assuming m is not changing, this is a multi-particle system, it's going to be fixed. So I can integrate this and I get this. But it depends on the initial and final values. Initial. So what did we show here? This is the work done by an external force on the center of mass. And what it's equal to is the change in kinetic energy of the center of mass. So that can be useful. It can be helpful. You can, figure out. So if there's an extent, if there's no external forces, like you only have internal forces, the center of mass velocity is fixed. If you have an external force, then it can move to center of mass, and you can treat it separately as if it's like, take this multi-particle system and just think of it as one point mass if you want to figure out what the center of mass is doing. So it doesn't mean the external force doesn't affect the internal distribution. So an example would be a star cluster moving in a galaxy. You can think of it as a point mass moving through the galaxy, but it can be on an orbit through the galaxy. It could be going on a circular orbit, or it could be having an epicycle because, you know, there's a acceleration due to the mass in the galaxy. But there could also be tidal forces. So tidal forces means the individual particles can be pulled a little bit with respect to the center of mass. So this calculation doesn't take that into account. All it does is tell you where the center of mass is moving to predict where the cluster goes in the galaxy. And then you can think it separately of the whatever going on with the particles inside the cluster. And if you want to, you can take into account the tidal force, which is tidal force means the gravitational force. It's not exactly external gravitational force. It's not exactly uniform everywhere. So with G, like vertical force down due to gravity, it's constant. It doesn't matter where you are. But if you go into space and think about force from the sun, you know, on one side of the Earth, it's slightly stronger than the opposite side. But if you subtract out the mean, then you get a tidal force which pulls and pushes. So you can think about that separately if you want to. Center of mass still behaves as if it were a point mass particle. Okay, so let's now kind of summarize for energy. So total energy. And it did it again. I mean, it's really helpful to rest my hand on this, but when I touch the bottom of the screen, it goes into these different modes. So total energy. So I'm going to neglect heat. So it's often to decompose it, the total energy. And so energy overall should be conserved, right? So when I say I'm neglecting heat, it's kind of like neglecting dissipative forces. But to decompose the total energy for a multi-particle system, we have the center of mass kinetic energy. And we call this the translational part. Then we have the relative kinetic energy. So this is each particle with respect to the center of mass. If it's a two-particle system, you can write it in terms of the reduced mass. And this includes rotation and vibration. And it could include tidal, you know, deformation, any kind of deformation. So what else do we have? We could have potential energy from forces in between each particle. So we have potential energy terms. From interparticle forces. You just sum all the pairs of particles and you would get the total potential energy from interparticle forces. And then if you have external forces, you have the sum of potential energies for that. So this should be it, right? So as long as you've got, you know, conservative forces, which, you know, fundamental forces are conservative, like gravity and electricity and magnetism. And so you should be able to keep track of all energy. And this ignores heat, but so that's the last piece. So sometimes energy gets put in the form of heat. So things go into excited states. So you can worry about that too. But for these classical problems, you know, we can keep track of the total energy. And it's just a sum of all these different things. Okay, so let's do a quick review of the formulas we've done in this section. So the center of mass. No. Center of mass. So we wrote center of mass in a bunch of different ways. And you can write it out as a sum over particle positions, where m is the sum over each particle total mass. So this is center of mass position. You could also write it as a interval over a density distribution, dV, where dV is a volume element, and rho, which is, is a mass density. And this is integrated over the body. So, and in this case, m is just the integral of rho dV, like that. The velocity of the center of mass, you just differentiate these. So we have, if we have a mass distribution, it would be rho v dV. And if it's a particle distribution, it's the sum mi vi, like that. This is a vector. Okay, so to continue reviewing, so the total kinetic energy for a multiple particle system, we can write in the sum of two terms. A translational term plus an internal term. And the translational term is that of the center of mass. And the internal term is the kinetic energies with respect to the center of mass. So it's VI minus V center of mass squared. And my notes are missing a small index there. So you can always do this. If you have a two-body problem, non-relativistic, then it's handy to write this as 1/2 mu u diff squared. And this is the reduced mass. So mu is m1, m2 over m1 plus m2. And u diff is the velocity difference between the two particles. And actually, I don't know, sometimes it's 1 minus 2. You have to, you can decide what the convention is. Another thing to review, internal forces. That means that when should we use reduced mass? When you have two particles. So two-body problem, molecule, then the reduced mass is handy. There are generalizations for higher numbers of particles, but they get kind of complicated. You have to decide whether you want to do hierarchical or not. So there's a whole system, like you can, for example, Jacobi coordinates for a three-body system or higher. You take the first two bodies, you work with the center of mass with respect to that. Then you take the center of mass of those two and you take the third body and you describe it with respect to that. Then you take those three bodies and you describe the fourth one in terms of the center of mass of the other three. So, so you can come up with hierarchical systems for describing things, and then you get generalizations of reduced mass, but these are more complicated. So usually just the reduced mass, it's not that complicated for two bodies problem. Okay, so internal forces alone. By the way, that was a pretty good question, because there's a whole fields of notation and different approaches to n-body systems. So getting back to what we're talking about, with internal forces alone, the total momentum is conserved. So that means this translational kinetic energy is conserved if it's a, so usually when you talk about kinetic energy, you're working with non-relativistic things, but the statement that the total momentum is conserved when you have internal forces alone is perfectly correct for a relativistic setting. So when you have external forces, you can think about the work done on the center of mass. So you can sum the total force, which is the sum of the forces on each particle, and the work done on the center of mass, which is the interval of this total force times integrated up over how far the center of mass moves. And this is equal to the change in the kinetic energy of the center of mass. And then lastly, we talked about thrust. So F thrust is equal to minus dm dt times V rel, where V rel is the relative velocity between your propellant and a rocket, for example, and dm dt is the outflow rate, the mass outflow rate of the propellant. So this is an equation you could use to calculate the acceleration of a rocket. Okay, so that summarizes center mass and multi-particle systems. And so it's like 10:40, so we have like a few minutes. So I'm going to start now talking about collisions. And then if we, been kind of a little bit behind on lectures, but I want to talk about, at some point, we'll slip in a little bit on conservation laws, which at the end of that set of lecture notes. But for the moment, let's move on and talk about collisions. So new topic, collisions. Oops. Yay. Okay, so what happens in a collision? So the basic setting is you've got some particle and it's moving at some velocity, and you've got some other particle and it's moving at some other velocity, and there's something happens and they whack each other. And then I mean, I suppose you could destroy these particles, but for the moment, let's talk about solid bodies that are going in and out of the collision. This guy reverses direction and it has some velocity afterwards. And this guy reverses direction too, and he has a new velocity. So this is initial, and this is final. So think two ping pong balls, or two ping pong balls hitting each other, or two billiard balls hitting each other. So firstly, let's think about what happens during the collision. So maybe easier, instead of thinking of two things hitting each other, how about just a ball hitting a wall or a floor? Kind of like lab 3, where you have a ball hitting the ground and then bouncing back. So so during the collision, so collision happens over some period of time, and there's a force, force on the object. And so let's think of a ball. It falls down and then it bounces back. So at the moment it hits the floor, it's starting to change momentum because there's a force on it. And so before and after, there's a big change in momentum. So so the ball itself, assume it doesn't lose any mass or anything, starts off with one velocity, ends up with another velocity. So there's a big change in velocity. So so let's think about what happens. What's the force as a function of time? So I can draw a picture like this. So it's force, time. So as it starts to hit, you get this really big force, and then it dies down. And if I integrate this force, so force is dp dt is equal to delta p. So I integrate all the forces from this time to this time. So this is the change in momentum. And so if the ball bounces back and no energy is lost, then it's going to bounce back with the same velocity. And so delta P will equal to 2mv, where v is the initial velocity if it's elastic. So yeah, because it's got the same velocity, but it's flipping sign, right? So that's where you get this vector of 2. And m would be the mass of the ball. So so often when we're thinking about collisions, we talk about the initial conditions, which is before this happens, and then we're talking about things after this whole process. So we assume that this thing, the force is a function of time. This thing is called the impulse. We often assume that it's short, and we're just going to ignore all the details in it and just say either it's elastic or inelastic. So elastic, what does elastic mean? Elastic means there's no energy loss. It's like you think of the ball as a little spring, it compresses, and then you get the energy right back out when it decompresses. But you can have anelastic or inelastic collisions that you lose energy. The ball could fracture. You could have air inside it heat up. I mean, so things aren't always perfectly elastic. So force, what if you want to reduce the force? So the total momentum change in this elastic thing depends on the integral here. So I could achieve the same change in momentum with a much longer impulse. And just as long as the areas underneath these two curves are the same, then they would have the same total change in momentum. So, but the difference between, so if you can slow it down, then you get less force, which is less acceleration. And so if you have a setting where something is being damaged by high accelerations, then you want to slow down the collision. So there are lots of ways to do that. You can have padding, you can have crushable foam, you can have fluids being excited, you can have airbags. You think of all these clever ways people have tried to improve safety of people inside cars during collisions. Too bad they don't actually help pedestrians or bikers that are hit by cars. But anyways, like me. But so this is in car crashes, adding things that spread out the impulse is done on purpose to protect people when they're in accidents. And so lab number 4, which you guys haven't started yet. So you guys did the coefficient of restitution of a bouncing ball in lab number 3, but and next week you're going to write that up. But the week after, lab number 4, you can use the force sensors in the lab to measure the impulse. And so so what I did this year is I got a bunch of I got some crushable foam, and you can look at how much force you need to crush the foam, and you can look at collisions with different velocities and the shapes of the impulse with putting foam in different configurations, how much area is being crushed and stuff like that. So hopefully it'll be interesting. The trick turned out to be finding a nice foam that's easy to crush. So I found some nice foam for you guys to play with. So that's lab number 4. It's a new lab, so doesn't mean it's perfect. So it'll be interesting to see what happens for lab number 4. Okay, so moving on. How much time we got? Oh, we still have 10 minutes. Good. Okay, so let's do a non-relativistic collision. Collision. We're going to make it as simple as possible. We're going to put it in 1D, 1 dimension. And we're going to make it elastic. So what do we got? We have M1. So, and it's only going to have 2 particles. So we have M1, and it's got some initial velocity, V1I. So that's its initial velocity. and it's going to hit some other particle here, which is m2, and it's got an initial velocity v2I. So, so I'm going to do this in general now without specifying a velocity for m2, but we're going to do the collision with m2 initially at rest. But for the moment, we're not going to assume that. Then, so yeah, so then they hit. So I guess if it's not moving, so let's put it here so it's not moving, it'll be like this. They hit. And then, when they hit, there's internal forces, right? So that means the center of mass velocity doesn't change. So I can figure out from the beginning, from these initial conditions, I can figure out what center of mass velocity is, and should be the same after the collision because internal forces, right? So then afterwards, things will bounce back. So this guy will go this way, and then this big one is not going to move as, not going to be affected as much because it's more massive. So maybe it has a smaller velocity. So this is going to have v1f as a final velocity, and this one is going to have v2f final velocity. So this is before, and this is after. And here's the collision. Okay, so since internal forces alone are happening during the collision, the total momentum is conserved. So that means the total momentum, which we can write out like this. That's the initial total momentum. Is equal to the final total momentum. So consider what happens if I divide both sides of this equation. So this is conservation momentum. So let's just divide both sides of this equation by the total mass. So why did I do that? Because this is the center of mass velocity. And it's equal to the center of mass velocity afterwards. So conservation momentum is equivalent to saying center of mass velocity doesn't change, not surprisingly. So it's just kind of, should make it easier to kind of understand what we're seeing there. Okay, so let's erase this because we don't need it right now. So if the collision is elastic, that means the kinetic energy, the total energy is the same before and after the collision. So the kinetic energy beforehand is this. And so it's v1I squared plus m1 1/2 m v2 v2I squared. And this has to equal the final kinetic energy. v1f squared plus 1/2 m2 v2f squared. So this is if elastic. There's two types of problems that we tend to do that are kind of fairly straightforward to do. One is elastic, which means you get this nice constraint from the kinetic energy. The other type of problem that's like pretty easy to solve is when the two particles stick together and then they just move at the center of mass velocity afterwards. So you'll see those types of problems a lot because they're like the easy ones. And things where you lose some energy but they don't stick together are much harder. You have to know, how much, and that makes it harder to solve. Okay, so we have these two constraints. So basically, based on the initial velocities, we should be able to use these two constraints, the conservation of momentum and conservation of energy, to solve for the final particle velocities in terms of the initial ones. So another constraint that I'm going to write down. So remember, with two particles, you can always write the kinetic energy in terms of the center of mass kinetic energy and the relative one. And sometimes that is, helps you. So I'll just write down, this might be more easy to work with in some cases, certainly more easy to work with if you have two particles that stick together. So it also looks like this. Oh, plus, this is plus U, and this is V1 minus V2, and it's either initial or final. This has got to stay the same. And this has to stay the same too, right? If it's elastic, may not be elastic, and this is the reduced mass. So sometimes it's helpful to write the kinetic energy like this too. Okay, so now let's take an initial condition, meaning we're going to specify that the second mass is initially fixed, and then we'll solve for the final velocity. So I'm going to call this in the lab frame. And we have an initial velocity for the first mass, which is, we're just given it. And then the second initial velocity is going to be 0. So why am I specifying in the lab frame? Again, one of the themes is that it can save you some time and energy to do the problem in the center of mass frame. So what do I mean by that? We'll talk about that, because I'm going to give some examples where we solve the same problem in different ways. So one way is to solve it in the lab frame, which is like, I'm just going to work with V1 and V1I, V2I, V1F, and V2F. It might be useful to compute the center of mass velocity, subtract it off from all the velocities, solve the problem in the center of mass frame, and then transfer back into the lab frame. So sometimes that saves you time. So in any case, we'll do this example we're going to do in the lab frame with the second mass initially at rest. So let's write down conservation of momentum. 1v1i is equal to m1v1f plus m2 v2f. So we lost a term because v2i is 0. So this is conservation of momentum. And if it's an elastic collision, we have conservation of energy. M2v2f squared conservation of energy, because it's an elastic collision. So now a bunch of manipulation. So so this one, so let's take the first equation. We can write m1 v1i minus v1f is equal to m2 v2f. So I just moved one term onto the other side. And then the second equation, get rid of these halves, they're kind of boring. M1 v1i squared minus v1f squared is equal to m2 v2f squared. But I can write this as v1i minus v1f times v1i plus v1f m2. So I just took this difference in squares and wrote it as a sum and a difference of terms. And then this, you can see this is equal to this, this is equal to this. And so I can write this as m2 v2f times v1i plus v1f is equal to m2 v2f squared. And then this cancels, and one of these cancels. And then if I could substitute in from inserting back into the first equation, then I can solve for v1f, and then I can use that and solve for v2f. So that's the final velocities for the two masses. So doing that, I'm just going to now write down the answers. So let's go back to the beginning. Oh, we got blank one. Good. So I'll write down the answers. v1f equals this. Times v1i, and v2f is equal to 2m1 over m1 plus m2 v1i. So these are the final velocities. How are we doing on time? Well, we're out of time, but that solves the problem. And so the next thing I want to do is look at various limits, so we're going to say, what happens if m2 is really big? Does it make sense? What happens if one of the velocities is really big? Does that make sense? What happens if m1 equals m2? Does that make sense? And then, so we'll take limits and show that these are kind of what you expect from, if they're equal mass, they'll bounce back, giving each other about the same momentum. And if one of them is really big, then it doesn't move, and v1 will bounce back with the same velocity it came in on. In any case, that finishes today's lecture, so we'll stop there. So I guess that ends class.
Thanks.
See you on Tuesday. Hope today's problem set goes well.
Thank you.
Bye.